So the final thing we have to do is consider manifolds that are covered by coordinate charts and that aren't themselves just Rn or the upper half space. So first, let's consider when the support of omega is contained in a single coordinate chart. So here we're thinking of coordinate charts as parameterizations. So we're thinking of these as maps from Rn into the manifold. So like Spivak theorem 5.2. Okay, so in this case, if omega, so the support of omega is contained in the range of some coordinate chart phi, and let's assume it's positively oriented. The negatively oriented case is exactly the same. You just change the signs. Okay, so let's also assume that it's a boundary chart. So let's assume that phi is a boundary chart. So we've got some boundary here. Okay, so if we just take the definition of what it means to integrate d omega over m, this is just the same thing as the integral over the upper half space of phi pullback of omega. That's just the definition, or sorry, phi pullback d omega. That's just the definition of the integral. And then I can switch the d and the pullback, as you remember from several weeks ago. And then because I'm now in the upper half space, I can reuse my computation before to get that this is the integral over the boundary of the upper half space of phi pullback omega. So the last thing that I need to do is show that this is the integral over the boundary of the manifold of omega. And that's going to be true because I can restrict, so I can restrict phi to a coordinate chart for the boundary of M. And the same thing will be true for an interior chart. It's just that, everything will be 0. So the same idea works for an interior chart. But we'll get 0. So that's what we want. Okay, so the final thing, so we've considered omega being supported in a single coordinate chart. So the final case is where omega is just supported by finitely many coordinate charts. So omega is supported in the range of, so in sort of some set of finitely many. So because omega is compactly supported, I can assume that it's supported in some finite set of coordinate charts. Okay, so we're going to assume those coordinate charts are called UI and they have parameterizations phi. So actually, it doesn't really even matter what the UI are, but the UI are the images of the parameterization of the images in M that are parameterized by the phi. So let's choose a partition of unity, subordinate to the cover by the UIs. And then we can just, it doesn't matter if they're boundary charts or interior charts, then we get that the integral over M of, the integral over the boundary of M of omega is equal to the sum over I over all the coordinate charts of the integral over the boundary of M of psi I times omega, just by how we define the integral over or actually, no, this doesn't have to do with how you define the integral. This is just because it's a partition of unity, right? Because at each point, all the psi's, when you add them up, sum to 1. And then I can use, so now these are on a single coordinate chart. So I can, because psi I is subordinate to UI, I'm now just on a single coordinate chart. So I can rewrite this as like I can apply my case 3, this previous case, to get that this is the integral over m of psi I times d omega. And right, that's because all of these computations are only occurring in either UI. They're occurring in the single coordinate charts UI, or the restriction of UI to the boundary, the restriction of those coordinate charts to the boundary of M. And so, oh, sorry, I swapped my D and my psi I. And then now by the properties of D, this is going to be D of psi I wedge omega plus, because psi I is just a function, I get a plus sign here, psi I d omega. And then I can rewrite this as the sum over I of the integral over M of D of, I can put the sum inside. So the integral over M of D sum over I psi I omega to deal with the first term, because D is linear and integration is linear. And then I get the integral over M of the sum over I psi I times omega. And this first thing is the integral over M of D of just 1 times omega. So D of 1 is 0. So I get this whole term is just 0. And then this is the integral over M of omega because the sum of the psi i's is 1, because it's a partition of unity. So now I'm done.